Hey everybody, my name is Emmanuel Jacob, and today I get to show you a little bit about a project that I've been working on. It's a multi-product deployment. This is for Liberty University Engineering 340, which is Operations Research Part 1. And let's go ahead and show you a little bit about it. So the idea of the multi-product deployment we'll get into a little bit. So the product description that we've got is initially we've got a multi-product deployment process in a single period. The objective is to minimize the sum of the transportation cost and the storage cost. The transportation costs include the regular costs for all flows and extra costs for the amount of flows that are in excess of the capacities of the links, and the storage costs are charged only for the amount of goods over the site capacity. Basically, in a nutshell, what that means is this model will show you have on-hand quantities in 7 different cities. We have links that are created between those 7 different cities. There is a link weight attached to each link. In other words, a kind of a cost to go down that link. There's also a link capacity, the number that you are able to actually go down. So, for example, from Atlanta to Chicago, there is a link capacity of 50. And you've also got storage capacity, so warehouse capacities. You've got extra cost for the warehouse capacity involved. I'm sorry, in warehousing or in site capacity. So this is a really good model, I think. It's a complex model. It's a really good model. So going on, for each article or product, as it's called, the program computes the flow of goods in each link between the cities or the nodes, in order to cover the demand. And there is a demand array as well in here, and minimize the total cost. It also provides the optimal acquisition plan for extra storage and link capacities. So some of the cities that we're talking about is Atlanta, Chicago, Dallas, Denver, Newark, Pasadena, Portland, and we've only really kind of given it 7 different links. So there are links between Atlanta, Chicago, Chicago to Dallas, Chicago to Denver, Dallas to Newark, Dallas to Pasadena, Portland to Dallas, and Portland to Denver. So that is basically a quick overview of the problem description that we're dealing with. So why did I choose this topic? In fact, this topic was very, very easy to choose just because of the fact that, one, it was complex, that's for sure, but it's really closely related to a transportation model. And the transportation model is a model really that you have hubs, and you have basically you have to deliver to and from these different hubs based on demand and different constraints. So it actually is really closely related to my winter internship that I'm kind of working on right now, which is optimization of the shipping department. That has to do a lot of the nodes, right? We've got a lot of places like at the dock. We've got storage. We've got deep storage. We've got, and then we've got capacities. How many can I move? How quickly do they move? What is my demand, expected demand? I get a lot of that information from it. So a lot of this information is very, very closely related to what I'm going to be doing in my winter internship project. The second thing is that this product deployment model is pretty similar because we've had something called, obviously transportation models, but also shortest path type problems are very similar to this. But it's also difficult because it's in OPL, or what we'll be using OPL CPLEX. Or IBM CPLEX, I'm sorry. That will be very, there's a big learning curve to be able to learn the way it sets up its arrays. It's a coding type program, based program. So learning how to use that properly and get the information that you want. There's a lot of syntax and a lot of other things you have to know how to do. So that'll be a big learning curve to be able to do that. And again, the reason I also chose the topic is because the companies that use these types of models, FedEx is a huge company, obviously, you're looking at using these types of models. UPS, Amazon. Amazon just started doing Amazon Prime Air, which they're deploying droids to start to deliver instead of using UPS or FedEx. Also Pizza Hut. Pizza Hut just recently started sending out droids to deliver pizzas. That was a new thing that just came out in the news not too long ago. And then you've got logistics companies like Hanjin. They're huge, huge companies that ship really large freighters all over the world, all over the world. So, and of course, obviously, the Department of Defense and the Department of Energy are just a few of the things that why I chose this topic. So the closeness to those types of things is really close. So the original model has 2 products between 7 cities, and they have designated weights in their transportation links between some of the cities. Each city has an on-hand or an initial number of product and a set demand. The objective is to move the product from each location to meet demand while minimizing cost associated with transportation and storage. And the constraints are basically demand is a constraint because we've got that set. Link capacity is a constraint because we've set that as well, and also site capacity. Considering then again we're doing, if we're doing a transportation model, you're doing demand, which is obviously that's going to be the same. Link capacity is, what are we shipping with? Are we shipping with trucks? Are we shipping with big trucks, small trucks, LTL, as well as site capacities? How big are my warehouses in each site? So it's a very, very, again, relatable topic. Basically, what I'd like to do is, the majority of the original model will be left intact. I didn't want to mess with a lot of the demand or mess with the other stuff, but what I wanted to do was change the weighted links to something a bit more meaningful. And I wanted to change it to mileage between cities. That's just the beginning of it, because in the end, by changing it to mileage, I can then start to set new constraints, like each driver will drive about 8 hours a day. That is customary for truck drivers. And then you can give them an average. How many miles do they drive in those 8 hours a day? If they average 65 miles an hour, 8 hours a day, you're looking at 520 miles. They have a capacity. After 520 miles, if your link is longer than that 520 miles, which we've already designated through our mileage, then we can go ahead and say we have to add more than one driver. So if it's, let's say, 700 miles, I need 2 drivers, which I pay at 30 cents a mile, and that's about generally what they get paid. So at 30 cents a mile, I now am paying 2 drivers to take one load because one would be constrained, and he can only drive 520 miles, and I need somebody else to drive the other 200 some miles to be within the law. So those are some of the constraints we're adding to it. So also, again, that driver cost per hour will come into the equation. We'll show you how I did that. So the mathematical model, it's fairly simple once you break it down. The code is about 130 lines, but it's fairly simple when you break it down. You're minimizing your total link cost and your total site cost. Your total link cost ends up coming down to the cost between each node, which we defined as our mileage. So basically $1 per mile is what I defined it to keep it easy, times my flow between those links. So basically, when I end up optimizing my flow, I get a number of times that the transportation model has to go. The transportation has to go between these nodes. So if I take cost times the flow plus my extra cost for if I have to, let's say, add more, so it's called a link extra set, link extra cost. I'm not going to change that. I'm going to leave that as is. Multiply by my link extra just to have more excess on that link itself. So that's basically the idea of my total link cost. My total site cost ends up being broken down as my site extra cost, which is if I would have to store more in a certain warehouse, I'd obviously have to store it outside of the warehouse, maybe in a trailer, in a real sense, in a different warehouse to rent out a warehouse, as well as, so my site extra cost times my site extra gives me my total site cost. So these are subject to really 3 different constraints. My first one is my demand, and my demand is basically my on-hand and the summation of my links going to a destination times my flow, which we talked about, which is a flow across from the nodes, minus my links to my origin times my flow. I have to make sure that my demand is less than those on-hand links. In other words, what I'm saying is I want to meet the demand and not send more than the demand. The second one is the sum of the articles. The articles, again, are the products. So the number of articles times the flow has to be less than my link capacity plus my link extra. And then lastly is my sum of the articles times the sum of the links, yada, yada, yada. So I'm not going to leave that free there. So what am I going to change? I I'm going to add a total driver cost, and that total driver cost is going to come down to really a, and I changed it a little bit in my model, but what I did was a cost function, cost times my flow times how much I have to pay per driver times 0.3, so 30 cents a mile. So because my cost is my mileage, I multiply my mileage by how much I pay a driver per mile, and then that's times flow, because if let's say I drive 20 times and it's 700 miles, then I do 20 times 700 is 1400 times 0.3 is what I'm paying per mile for a driver cost. So that's kind of what I've done in my constraints. So now going over to my CPLEX code, I'll show you exactly what it looks like before. Now before, really quickly, we'll go through. A lot of the beginning is really configuration, defining variables like links, on-hand quantity, on-hand sets, demand sets, and whatnot. Defining our float variables here. A lot of this is just defining it. The beginning of this is really defining a lot of our expressions just to get down to what we're looking at here is our minimization. This is a minimization. We got a total link cost and a total site cost. Total link cost is broken down even further into a cost of each link, which is defined on the left here. So if I look at link right here, sorry, cost. Now each link cost me 2212111. Basically is because the first link between Atlanta and Chicago is 2, Chicago and Dallas is 2, and stuff like that. So what I've done is left that as is. Obviously this is the original model. Let that run, and I minimize, the original model says to minimize these things, and it gives me 3 constraints. Constraint of link capacity, which is my flow between that my products move, has to be less than or equal to my link capacity and my link extra, this is just a cost associated with if I have to go put extra product down that link. And link capacity is just really what I can put down that link, which is set right there. All right, so I've done that, and what I end up having is a total link cost of 310, a total site cost of 570, for a total of 880. Now I've changed it in my model, and really quickly what I've done is, first of all, I added a driver cost. You can look at my cost function here as well, and you can see that I've actually changed the values. Instead of 2212111, I've actually put in the values for the mileage. So then, when I put the value for the mileage, I can look at an expression. So I had to add a driver cost here to make a driver cost set, because if you look at my data file, I had to now add a driver cost set, which means from Atlanta to Chicago, I need 2 people. From Chicago to Dallas, I need 2 people, because I can only do 30 cents a mile at 520 miles per driver, which is what they can drive in an 8-hour set. So then when I've added this right here, which is my total cost now, because my minimization function is now total link cost plus total site cost plus total driver cost. And my driver cost is basically the cost, which is $1 per hour, $1 per mile, times 0.3, which is how much it costs for the driver itself, times flow, so where it's gone through. And now once I've done that, again, since I've changed a lot of and customized it, I've left everything else the same down here, I've now got a different solution. What it now tells me is my total site cost obviously is going to stay very close to the same than what it did before. My link cost has now changed, and so is my total driver cost. So this is the way that I've customized OPL CPLEX for IBM. Thank you.